Okay, my friends, so let's finally get around to constructing some of these confidence intervals from scratch, from data, rather than just being given stuff. If you remember back to one of the first videos I made for this class, I was spinning pennies on a table outside of my office. And if you remember, if you probably don't, which is okay, because I had to go back and look it up myself, I spun pennies 20 times, and I got 5 heads and 15 tails. Because I remember in the video I made a statement that means I got 25% heads, which is exactly what that is. And that seemed kind of odd, right? That seemed a little bit odd, because when you flip coins, they generally happen at 50-50. Now, could you flip coins and get the result 5 heads and 15 tails? Absolutely. Not very often, but it can happen. But spinning them is a new way of kind of turning over coins to get the results heads and tails. So then a question is, based on that sample, are spinning pennies different than flipping pennies? I don't know. And that's where we start today. Today we're going to start learning how to estimate a population proportion. Here's the thing. We know that somewhere in the universe of physics, there is a proportion. There is a proportion that represents the chance of heads. Excuse me. On a spun penny. We know that. We just don't know what it is. It's an unknown parameter. We can assume it's 50-50 and then collect data and test that, which is actually what we're going to do right now. So we're not ever going to know what the actual population parameter is. However, we do have a sample proportion from this study, a very small, ill-funded study, but a study. 5 heads out of 20 total spins. 5 heads out of 20 total spins is 25%. But we can't say that that is equal to that. We've talked about that over and over again so far. So what can we do? We can put the margin of error around it. We can take that p hat and add and subtract the margin of error. Now, I'm going to place a video at the end of this playlist justifying what I'm about to write on the board. Justifying what I'm about to write on the board. Because the formula for the margin of error for a sample proportion is a little bit to look at. It's a little bit much. But don't worry about it, because I'm going to justify why it works in the very last video, in an optional video if you're interested in the mathematics. If you're not interested in the mathematics, you don't have to watch it at all. So what I'm going to do real quick is I'm going to clear the board, and then we're going to rewrite this up top and give you the formula for that margin of error. Okay, so p hat sample proportion. Here we go. Drum roll, please. Margin of error for a sample proportion is given by this calculation. Confidence multiplier, which we call Z, times the square root of p hat times 1 minus p hat all over the sample size. That, my dear friends, right there, is how you calculate a margin of error for a sample proportion. It's the plus or minus. The plus or minus around the statistic. So you got your statistic, and you've got that offness that we use to pad the statistic. So what we're going to do now for our sample of size 20 is we're going to plug numbers into this puppy dog, and we're going to see what numbers come out. So we're going to start with p hat. P hat was 25%. So that's the center. Okay, Z is the confidence multiplier. I'm going to go ahead and use 1.96. That was that. I know we in the last video we said it was close to 2, but it's still 1.96 times the square root of p hat, which is 0.25, 1 minus p hat, which is the other 0.75, over 20. Close the parentheses off there. Okay, so now I think it's time to go to a calculator to figure out what that mess is, and then we'll come back here. Okay, my friends, so let's, I'm going to use Google as a calculator here. It's 1.96 times square root is SQRT, in case you didn't know that, times 0.25 times 0.75 divided by 20. Okay, I'm going to press enter on this puppy dog. That right there is our margin of error. That's essentially a 19% margin of error. If you round that off to the nearest percentage, that's a decimal form of a percent. As you may have noticed, I was using that on the screen up there, on the chalkboard. So we're going to have to round this one off to the same. So that's going to be a 19% margin of error. Okay, let's go back to the board. Okay, my friends. So now we know that our p hat was 25%. The margin of error is 19%. That means we can put these two things together and come up with a confidence interval. So, if we subtract 19% from 25%, we get 6%. And if we add 19% to 25%, we get 44%. So what does this tell us? I'm 95% confident that if I spin a penny, the actual percent that I get of heads is going to be between 6% and 44%. Let's think about that. That's kind of cool, actually. That's way lower than it should be. I mean, if we're comparing it to flipping a coin, right? If we're comparing it to flipping. Flipping would be 50%. This is significantly below 50%, right? Because 50% is not in the interval. 50% is over, if you picture this on a number line, 6 to 44% is here, and 50% is over here. So this is actually statistical evidence that spinning a coin is different than flipping a coin. The only thing that's bugging me is that I only did 20 trials. Maybe we should do some more. Let's go do some more.